Sitting by a window in a light rain, you draw a square on the glass to count how many raindrops hit it every 10 seconds. Will the same number of drops hit the glass every 10 seconds? Could there be 0 drops in one interval and suddenly 5 or 6 in the next? In everyday conversation, we label a process like this random. We use that word to describe things that are messy, completely unpredictable, or devoid of meaning. Questioning that assumption is how we find structure in the noise. Observing rare events over fixed intervals of time or space reveals a highly predictable, mathematical reality. We can track this structure anywhere we count things. How many cars pass a school crosswalk in a single minute? How many typos make it onto a printed page? To see how this works, we can run a physical experiment. Take a box of bran cereal, mix it well, and pull out 30 separate scoops. For each one, count the exact number of raisins. If you write down the results as they happen, you get a raw list of counts. Some scoops have 1 raisin, some have 4, and the numbers jump around wildly from trial to trial. Staring at a wall of raw numbers feels like looking at pure noise. To perceive the architecture hidden inside the data, we need a better tool to organize it. Instead of reading the numbers in the order we scooped them, we can sort them by value. We take all the scoops that had exactly 0 raisins and group them together, then do the same for 1s, 2s, and so on. By building a frequency table, we log exactly how many times each specific count occurred across our 30 trials. Those scattered individual counts lock together to form a distinct mountain-like shape. This histogram charts our raisin counts. The horizontal axis shows possible raisins per scoop. The vertical axis measures how often each count happened. Notice the tallest bars sit precisely at 2 and 3, while counts of 0 or 5 barely register at the edges. A single trial is noisy, but when we collect enough data and stack repeated random events together, a stable geometric pattern emerges. That mountain shape has a center of mass. If we total all the raisins from our 30 scoops and divide them evenly, we find a balance point, an average rate of exactly 2.5 raisins per scoop. In statistics, this steady average rate is represented by the Greek letter lambda. Lambda acts as the engine for the Poisson distribution. By plugging that single average rate into the formula, we generate a predictive curve that maps perfectly over our frequency data. This model applies to open, continuous intervals, like a volume of cereal or a block of time. If we count the number of 6s rolled on exactly 20 dice, we use a different tool, a binomial model, because the attempts are rigidly capped. Identifying a single variable, the average rate, grants us the mathematical power to accurately predict the likelihood of an expected result, or a seemingly unexpected extreme. A mathematical model is only useful if it matches reality. The Poisson distribution requires 3 strictly defined conditions. We must have count data, a fixed interval, and a fairly steady average rate. Tracking meteor sightings per hour during a clear night fits perfectly. The events are independent, the time window is set, and the meteors arrive at a fairly constant pace. But if the events are forced into groups, the rules break. Counting cars crossing an intersection right after a traffic light turns green violates the rule of independence because the signal artificially clusters the cars together. We do not blindly apply formulas to spreadsheets. Applying a mathematical model is a deliberate choice, requiring careful alignment with the physical world. If you sit by the glass and look at the rain again, you aren't looking at water hitting an arbitrary square. You are watching a steady rate play out across a fixed interval. An individual drop is uncertain, but statistics tells us that uncertain in the short term does not mean patternless in the long term. Zooming out and observing events over time strips away the noise. What looks like pure chaos up close is actually a universe operating with deeply predictable architecture.